Hello everyone, I am Valeriy Avanesov. Let's discuss data-driven confidence bands for distributed nonparametric regression. But some preliminaries first. I heavily rely on a concept of a reproducing kernel Hilbert space. First, let there be a compact X from a d-dimensional Euclidean space with a continuous measure defined over it, denoted pi. Also, let there be a covariance function k, symmetric and positive semi-definite. We denote its eigenvalues as mu sub j and eigenfunctions as phi sub j. The reproducing kernel Hilbert space is a subspace of L2 space of functions, endowed with the norm defined like that. What's important is the dot product is taken with respect to the measure pi. Easy to see that that a function with a faster eigendecay induces a smaller kernel, reproducing kernel Hilbert space, including smoother functions. The setting is fairly standard. We consider n data points, n pairs of response and covariate. Response is univariate. Covariate is, generally speaking, multivariate. It comes from the compact X, and all the covariates are drawn independently with respect to the measure pi. Pi is unknown. The responses are the values of some unknown function f star being corrupted by noise, which is believed to be sub-Gaussian, independently identically distributed, with some unknown variance. A classic approach to the problem is kernel-rich regression, which is effectively just ordinary least squares with a carefully chosen penalization defined in terms of the norm of the reproducing kernel Hilbert space induced by some covariance function k, which needs to be chosen manually as a hyperparameter of the method. The solution can be also obtained analytically. Pros of this approach include frequentist minimax-optimality. But on the other hand, the method does not yield confidence bounds and is fairly small, as one needs to invert n times n matrix. And the distributed implementation is also quite difficult. One of the remedies is divide and conquer approach. Namely, we just split the dataset into p disjoint partitions, obtain local estimates f hat sub p at each partition independently, and then just average them. Obviously, this algorithm enjoys embarrassing parallelism, and it also drastically reduces the complexity. The goal of this talk is to construct a ball around f star, L2 ball, such that it covers the divide and conquer estimator with a predefined probability beta. The problem here is that we do not have an access to the probability measure p. As a solution, we suggest to resample the local f hat sub p, the local estimates. Namely, we just draw uniformly and identically from the set of the local estimates p bootstrap counterparts. Then we just average them, obtaining the bootstrap counterpart of the divide and conquer estimate. The idea now is to choose this bootstrap world quantile and use it instead of the real one. The idea is that the bootstrap counterpart deviates from the bootstrap counterpart of divide and conquer estimator deviates from the divide and conquer estimator in the same manner as divide and conquer estimate deviates from the true function. But in order to assert this, we make some assumptions. First of all, we need to control the eigendecay of the covariance function. And also we impose assumption of uniform boundness of the eigenfunctions. As a motivating example, we use the Matern kernel, which satisfies these two assumptions under some conditions. The more problematic assumption is believed to be the second one, boundness of eigenfunctions, yet there is hope it is actually relaxable. As it was mentioned before, we also impose sub-Gaussianity for the noise. So we just assume that its tails are lighter than the tails of Gaussian distribution. I'm fairly certain everyone is familiar with bias variance trade-off, but just to make sure we're on the same wavelength. The expected error of a regression model can be decomposed into two terms, deterministic one and the random one. The first one, deterministic one, is describing the discrepancy between the set of models you consider and the true function f star. While the second one incorporates all the randomness from the dataset. Naturally, the richer the set of the models under consideration is, the smaller the bias get terms. The smaller bias term gets, and naturally this increases the variance term. Under normal circumstances, we wish to obtain the balance of the two terms, making them effectively equal. But not in this case. If we strive for construction of confidence intervals, we have to go for variance term dominating the bias term. In order to get ourselves into this situation, we have to use the kernel, which is too rough for the function f star. So the bias term will vanish. A bit more formal, let there be the covariance function k, whose eigendecay is driven by s, and we use this covariance function for the kernel rich regression. Then we consider a possibly smoother kernel k prime, whose eigendecay is driven by s naught, with s naught being not less than s. And let the true function f star be from the reproducing kernel Hilbert space induced by the kernel k prime. Abbreviate the above as f star belongs to h s naught. The first result is consistency result for the classic kernel rich regression. It says choose the penalization parameter properly. Then we have this high probability bound for the error term. The first term corresponds to the variance. The second one corresponds to the bias. What's important here, if S0 is above S, the first term dominates, the bias vanishes, exactly as suggested. This result handles consistency of f bar, the divide and conquer estimator. It obtains the same high probability bound, but we will naturally need another assumption here. The number of partitions should not be too large. But the good thing is that for highly smooth functions belonging to a reproducing kernel Hilbert space, induced by smooth covariance functions with large S with fast eigendecay, P can be chosen to be only marginally smaller than linear. Thus, we can bring the computational complexity to almost linear. And the main result of the paper, Bootstrap validity for the proposed Bootstrap scheme. Here we will need to impose undersmoothness assumption, so S0 is strictly larger than S. Again, we properly choose the penalization parameter, and we can bound the discrepancy between the real-life ball and the Bootstrap ball. The first term gets smaller with larger P, and the second term gets smaller with larger n and larger gap between S0 and S. The good question here is whether we can choose P in such a manner that both the previous theorem gives good results and this one gives good results. It turns out that such a choice is possible for S0 above 3/2. Recalling our motivating example with mature kernel, it turns out that the only setting left aside is a univariate case with mature kernel smoothness of 1/2. But hey, we've lost minimax-optimality, really, if the function belongs to smoother kernel Hilbert space. Why don't we just use a smoother function, right? The thing is that we do not have to choose s smaller than 2/3 of s naught, as this does not improve RB, the error term from this theorem, anymore. So effectively, we have this rate of decay of the error instead of the minimax optimal one, just replacing 1 with 3/2. This loss is marginal for s naught, for large s naught. A couple of words about the proof. First, consider the best penalized estimator, the one you would have theoretically arrived to if you had an infinite dataset. All approximations will be uniformly over positive radii of the balls. First, we do Gaussian approximation for f bar with Gaussian element gamma for some deterministic a. So we have ball on the left-hand side, ball on the right-hand side, but gamma is Gaussian. The next step is to do Gaussian comparison, leaving only the centered Gaussian element on the right-hand side. No, there is no a on the right-hand side. While on the left-hand side, we have f star, the true function, instead of the best penalized estimator. So on the left-hand side, it's the norm of a non-centered Hilbert element. Now the same thing goes for Bootstrap world. So yet another Gaussian approximation. And finally, we can do Gaussian comparison for gamma and gamma hat, thus establishing the claim. Now, an example: consider a unit interval to draw covariates from. The smooth function f star, quite a bit of noise, and bimodal distribution for the covariates. So we'll have more data points closer to 0 and 1. The confidence level is chosen as 0.95. Here we have the black line for the true function f star, red line for f bar, and the green dotted lines denote the Bootstrap counterparts of the divide and conquer estimator. Naturally, as expected, we have more uncertainty closer to the middle of the interval, and we're more certain about the predicted values closer to the ends of the interval. And finally, the simulation study. Consider a data set of approximately 130,000 data points. Again, a unit interval, but this time the covariates are drawn uniformly. The function is the same, the noise is the same, and the number of partitions runs from 2 in the 6th power to 2 in 13th power. The confidence level is chosen at the same level. First, forget about the red line, look at the blue and green one. Blue line represents the root mean squared error, while the green line shows the Bootstrap quantile. Naturally, they both grow for excessively large p, as it violates assumption of the consistency result. And the quantile R beta dominates root mean squared error because it's naturally a 95% confidence, 95% upper bound for root mean squared error. Finally, the red line shows the actual probability for the ball constructed via Bootstrap to cover f star. We can easily see there is quite a wide range of p to choose from. So we can enjoy both Bootstrap validity and optimal root mean squared error. Many thanks.